All right. So as I announced on Slack as well, right? So what we're going to do today is an extremely important property, which is the convolution property. And an extension of this is going to be the multiplication property, which is going to follow up this one. Convolution property is, and there's a separate section, I think, which is dedicated to this in the textbook. And the reason, of course, is because it's so important. And this is what leads to something called frequency selective filtering, right? So just to set things up, if I give you an LTI system, right? So let's say there's an LTI system, the input for which is x of t, as the notation that we've been familiar with, which is input to an LTI system which has an impulse response h of t, right? And the output turns out to be equal to y of t. And we know that in the time domain, y of t is just simply equal to the convolution of x and h, right? So the question we want to ask here, as far as this, the Fourier transforms are concerned, is I know that in the time domain, there is a relationship between the input and the output. And that relationship is the convolution relationship. And so in the sense that the output is the input convolved with the impulse response of the LTI system, right? We want to determine the same relationship between the Fourier transforms of the input and the output, right? So that's what this convolution property is about. And it leads to something which is very, very nice, which is very easy to evaluate. And there's lots and lots of implications, as we're going to see, right? So the problem statement is the following, that if x of t has a Fourier transform, which is equal to x of j omega, denoted by x of j omega, and the impulse response has a Fourier transform, which is equal to h of j omega. And this h of j omega, by the way, is often called, as we've done in CEP as well, and some other examples, this is called the frequency response of the LTI system, right? Which is just simply the Fourier transform of the impulse response, okay? And let's say if there's, the output is y, right? And that y has a Fourier transform, which is given by y of j omega, right? So the question we're really asking is, what is the relationship? So what is the relationship between x of j omega, y of j omega, and h of j omega, right? So that's what we're asking, right? Now, if you recall from our discussions on Fourier series, when we said that the exponentials, complex exponentials, are eigenfunctions of LTI systems, right? What was that relationship that we saw there? We said, KG, the output, if the input is a periodic signal, right? We determine that the output is also a periodic signal. Or output ke Fourier series coefficients, how were they related to the Fourier series coefficients of the input? Right? Anyone? So how were the Fourier series coefficients of the output related to the Fourier series coefficients of the input when the input was a periodic signal and the system was LTI? Right? So Daniel, what do you mean by inversely?
सर मैं ग्राफ्स कंपेयर कर रहा हूँ दोनों के, तो एक अगर नैरो सा था तो फिर दूसरा काफी वाइड था, ब्रॉड था, स्मूथ सा था, एक शॉर्ट था।
हाँ, लेकिन वो तो आई थिंक व्हाट यू आर कंफ्यूजिंग दिस विद इज के जी, अगर टाइम डोमेन सिग्नल है और उसका फोरियर डोमेन फोरियर ट्रांसफॉर्म है, एंड देन हाउ आर द रिलेटेड के जी, वन इनवर्सली इन द सेंस के यू एक्सपैंड वन, the other compresses. Is that what you're referring to?
Yes, sir.
Yeah, what I'm referring to is something else, which is KG, let's say there's an input signal, periodic signal, right? Uske Fourier series coefficients A hai. The output is also a periodic signal, uske Fourier series coefficients B hai. How is B related to A? And this was in exam 2, this was in CEP, this was in the homework, this was in the clinic that we did just before exam 2.
So h of j omega multiplied नहीं हो जाएगा उसकी coefficient
से? Yes,
से?
right. So we saw that the Fourier series coefficients, as Hassan Shabir also pointed out correctly, the Fourier series coefficients of the output were equal to the Fourier series coefficient of the input multiplied by h of j omega evaluated at that particular omega, right? Now, what we're going to do here, as far as this property is concerned, is going to be a generalization of the same principle, right? So we're going to see that once again, the output in the Fourier domain is going to be the input in the Fourier domain multiplied by the frequency response of the system. So that's essentially what the convolution property is about, right? And let's try to derive that relationship from scratch, right? So what we're interested in is, the question, of course, is what is y of j omega as a function of the x of j omega and h of j omega. Now, y of j omega, I know, is the Fourier transform of the output, right? Now, if I want to build that relationship between x of j omega and y of j omega, what do I do? I mean, what should be the next step here? What should be the next step? Right? So Hassan says replace y with its Fourier correlation, Fourier coefficients, but y is not periodic. That's the first point, right? So over here, what we're saying is that this thing is not necessarily periodic. It may be aperiodic. And in general, actually, it's going to be, most of the times, it's going to be aperiodic. Right? So the Fourier series coefficient, the Fourier series decomposition does not exist for the x of t. Right?
पर सर जो हमने कहा था कि a of k यानी कि जो आउटपुट के कोएफिशिएंट्स होते हैं वो इनपुट के कोएफिशिएंट मल्टीप्लाइड बाय h of j omega होते हैं, तो वो aperiodic signals पे भी अप्लाई होता है? यानी कि wasn't that argument based on periodic signals only?
That's exactly what I'm saying. That argument was based or was applicable only to periodic signals. Now we're generalizing that results in the sense that we're now talking about aperiodic signals. ठीक है? तो वो हमने जो पहली चीज की थी, अब उसकी generalized results हम निकालने लगे हैं, right? So let's see how is that applicable to aperiodic signals.
जी sir.
Right? So y of j omega is equal to the Fourier transform of y of t, right? What is y of t as a function of x of t and h of t? Right? That's given by the convolution relationship, right? Right? So I know that y of t, so I know that y of t is equal to x of t convolution with h of t, and the definition for that is this x of tau h of t minus tau times e raised to, times d tau. Right? This is what the input-output relationship is. Okay? Right. So Hassan, guess to that result. I mean, Hassan Shabir, ये आपने जो result निकाला है, I mean, is that based on intuition or did you go through this analysis to come up with this?
So just an intuition.
Right. So your intuition is correct, and that's where we're going to be headed, right? As we're going to see. Okay. All right. So this is y of t. Let me just plug this back in, right? So if this is equation 2 and this is equation 1, let's plug in 2 and 1. Right? And from here, what I'm going to get is y of j omega. Now I'm going to have two integrals. One of the integral is going to be over t. The other one is going to be over tau, right? So this is another integral here, minus infinity plus infinity. This is x of tau times h of t minus tau times d tau, and times e raised to the minus j omega t times dt, right? So essentially, all I have done is this thing inside here, this pink brackets, is essentially y of t, right? So, right, that's all I've done. Right, what do I do next? I mean, what kind of a manipulation could I do to get to the result, that intuitive result that Hassan points out in the chat box? I mean, does this now look something like the Fourier transform? Are there elements of the Fourier transform in here somewhere? G Abdullah.
सर जो
So this is Fourier transform of y of t.
This is the Fourier transform of y of t. Yeah, वो तो हमने starting out किया था ना. So I wanna बना तो फिर मैं यहाँ से इस equation से वापस 1 पे चला जाऊँगा.
Oh, अच्छा.
Right, so that I wanna go somewhere else, right?
सर जो आपने जो है पूरा we need to change it to x of j omega into h of j omega, right? Like
Yeah,
जिस तरह से
yeah. चलें ये इसी तरह कर लें. So this is going. Remember, लेकिन just you should try to appreciate the fact that Abhi, if I give you the result, then proving it is a lot easier, right? Because you know what you're trying to do.
yes sir.
लेकिन
yes.
असल में इस तरह नहीं होती चीजें, right? So when these theories or these results were developed, that's now how they went about it. That's not how they went about it. I mean, the forward
Yes,
direction is always more challenging, which in hindsight looks a lot easier.
Yes
Right?
sir.
Ji, Hassan, you want to say something?
I think we can do a substitution of t minus tau. तो हमारे पास एक exponential एक और आ जाएगा जिसमें हमारे पास tau आ जाएगा, and then we can use that.
Yeah.
And क्योंकि हमारा linear होता है integral, तो we can move that in.
Right. Excellent. Right. So this is what I'm going to do. I'm going to change the order of the integral because integrals are linear, right? So I can flip them around, right? So I can have x of tau come outside, right? And then I have an integral here inside, which is h of t minus tau times e raised to minus j omega t times dt. And once again, this is only because of the linearity of the integral operation, right? So this is inside the brackets here, and then the outside integral is with respect to tau, right? So I've just changed the order of the integral. Now the outside integral becomes with respect to tau, the inside integral becomes with respect to t, right? Now, what do I have inside these green brackets here? ये क्या है? Anyone? Right, so I've marked the CPU of 4 students already. Let's see if the other 10 can. कौन रह गया? Right, so what's inside this bracket here?
Sir, I think h of j omega होगा लेकिन with a shift.
With a shift, okay, excellent, right? So h of j omega with a shift. What do you mean by shift? The shift is in the time domain, right?
Yeah.
Right, so this green thing inside the brackets is the Fourier transform of h of t minus tau, where t is the independent variable and tau is some constant as far as this thing is concerned, right? And as Abdullah points out, there was a slight bit of an error there. Excellent. Actually, Daniel is, okay, वहाँ पे भी slight bit of an error, Daniel. Right, so this is equal to h of j omega and e raised to power minus j omega tau, right? So Daniel, you had a minus missing there. And Asad, you had right, Hassan Shabir is now correct. Abdullah, you had instead of t, we should have tau here because the shift is equal to tau. It is not equal to t. All right. So this thing inside this green brackets here is h of j omega e raised to power minus j tau. And therefore, this becomes equal to integral. So let me skip a line. This is integral minus infinity to plus infinity x of tau times h of j omega times e raised to power minus j omega tau times d tau. And therefore, h of j omega comes outside because it's just a function of omega. And this is minus infinity to plus infinity x of tau e raised to power minus j omega tau d tau, right? So Tareem, what's in this integral here? What is this equal to? Umar?
Sir,
Tareem, yes, go ahead.
I don't remember. Sorry.
Okay.
So x of j omega.
Right, so this is x of j omega, right? Hassan, you wanted to say the same, I believe. Right, so this is x of j omega. Now, so therefore, this completes a proof. This is or the derivation of the result is not a proof per se, right? So this is h of j omega, right? So what that means is that y of j omega, which is the Fourier transform of the output, is equal to the product of the Fourier transform of the input and the Fourier transform of the impulse response of the system or the frequency response of the LTI system, right? So, and that's an extremely insightful result, or a result that spawns so many applications, right? So what we've concluded is the convolution operation in the time domain. In time domain, if you take two signals and compute the convolution in the time domain, this is equivalent to multiplication in the Fourier domain. In the Fourier domain, right? Which is an extremely important result. Extremely important result. So many applications, right? Some applications I'm going to talk about, or one or two applications I'm going to talk about. Okay. Now, you could also, Umar.
सर जो h of t minus tau है, जब हम उसकी कन्वोल्यूशन करते हैं तो वो tau का फंक्शन बन जाता है ना?
When you have integrated it with respect to t, then afterwards it becomes a function of tau. Yes, I agree.
तो जो उसमें टाइम शिफ्ट हो रहा है वो t का हो रहा है, tau का नहीं हो रहा.
Yes, exactly.
तो e minus
sorry. उसमें टाइम शिफ्ट जो है टाउ का हो रहा है, t का नहीं हो रहा.
लेकिन वो tau का फंक्शन है तो कांस्टेंट फिर t नहीं होगा.
नहीं, you see, देखें, this thing here, which is inside the these green brackets here, right? You can see my cursor here, right? So this thing is here, which is inside the green brackets. What variable are you integrating over? You're integrating over t, right? So this is a Fourier. When we're computing the Fourier transform, the Fourier transform is being computed with respect to the independent variable, which is t. ठीक है?
ठीक है.
Right?
इससे पिछले स्टेप में लेकिन आपने उसको tau का फंक्शन बना दिया था, फिर अगले में वो t का हो गया.
Yeah, so it's a matter of perspective, right? Depends on what you're integrating over. Right? So I just see that over here I'm integrating over t, and if my integration is with respect to t, then all other variables besides t are constants as far as this integral is concerned. Okay. So then I would treat this tau as the shift basically, and as a constant as far as this integral is concerned, even though it becomes a variable, independent variable outside of this integral. ठीक है, जब यहाँ पे पहुँचता है उमर, यहाँ पे पहुँचता है तो this is same as tau, right? So here this tau is that independent variable जो कि x of j omega के बराबर होता है, right? So this is a play, a manipulation, if you will.
Okay.
Matter of perspectives, right? Okay, right. So what I wanted to say a little bit more is that some of the properties, or actually all of the properties that we did for LTI systems, whether that be associativity or whether that be commutative property or distributive property over addition, I mean, all of those should click together in the Fourier domain as well. And it should make sense that this must be a multiplication, right? So first off, for example, was commutative. We said that x of t convolved with h of t is exactly the same as h of t convolved with x of t, right? And indeed, this should make sense, because if you go in the Fourier domain mein convolution is the same as multiplication, right? And we know that multiplication is commutative, right? Therefore, x of j omega multiplied by h of j omega must indeed be the same as h of j omega times x of j omega. So everything clicks together. Okay? Does that make sense, right? I mean, so there's this jigsaw puzzle thing I talked about as far as learning is concerned, right? So you know some things, right? And then you learn something new. That something that you learned new should fit into your prior understanding, right? So your prior understanding was that convolution is commutative, right? That means x of t convolved with h of t must be the same as h of t convolved with x of t. And now we've learned that convolution in the time domain is the same as multiplication in the Fourier domain, right? So if it's multiplication in the Fourier domain, then multiplication we know is also commutative, and then everything clicks together, everything fits together. इसका मतलब convolution indeed जरूर commutative होनी चाहिए थी, वरना ये multiplication ना हो सकती. यहाँ पे for that matter you can say कि multiplication, क्योंकि ये multiplication है, because multiplication is commutative, and therefore convolution must be commutative as well, right? जी Zan, you had a question?
जिससे सर मैं ज़रा सा कंफ्यूज हो रहा हूँ सर. हमने एक प्रॉपर्टी पढ़ी थी जिसमें हमने कहा था कि y of t इक्वल्स टू एनी कॉम्प्लेक्स एक्सपोनेंशियल मल्टीप्लाइड बाय h of s, जहाँ पर वो h of s था वो एक प्रॉपर्टी थी. अब यहाँ पर हमने जो ये पढ़ी उनके तरफ लाइक दोनों को कंफ्यूज करा था. दोनों फर्क है ना, लाइक वो था पीरियोडिक सिग्नल्स के लिए और ये सब पे अप्लाई होता है,
और ये उस पीरियोडिक सिग्नल पे भी अप्लाई होना चाहिए. इसका मतलब you can derive that result from here. How so? Let's say, and then we've covered enough for the following question to be legitimate question on an exam. I mean, I'm sorry to say this, but that's the only way I get attention of people, right? Which is, I say, KG, prove using the multiplication property that complex exponentials are eigenfunctions of LTI systems. This is a legitimate question now. How would you do that?
So जो ऊपर में derivation है उसमें I need to replace x of this with a complex exponential, और फिर eventually ये वाला result derive हो जाएगा कुछ.
Right, और उसका Fourier transform निकालें, right? So Umar, do you have a question? या आपका हाथ खड़ा हुआ?
No sir, वो पहले से ही था.
All right. So I can do this here, right? So so exercise is the following. Right. So use the multiplication or the convolution property, actually, the convolution property to prove that e raised to power j omega naught t is an eigenfunction of an LTI system. Right? Remember from our analysis earlier, we know that e raised to power j omega naught t as an input to an LTI system results in an output which is equal to what? Which is equal to e raised to power j omega naught t times h of j omega naught. The question is, can you use the convolution property to prove this? So who's going to help me here? क्या ख्याल है? How do we use the convolution property to prove the statement that I just wrote?
First we'll step सर वो integral बनाएंगे.
Okay. Convolution. Okay, so that's what Abdullah. What you're headed towards is actually what we used earlier at the very beginning, just to prove that this is true. I'm saying कि आपको अगर पता है कि convolution property is कि y of t, if y of t equals x of t convolved with h of t, then I know that y of j omega is the same as x of j omega times h of j omega, right? Right?
अब मैं x of t को x of j omega बनाऊंगा और वो e के पास j omega not t आ जाएगा, तो वो प्रूफ नहीं हो जाएगा एग्जाम से.
Right. So x of t equals e to the power j omega naught t. But what is the Fourier transform for that? I would need to know the Fourier transform. What is the Fourier transform for e to the power j omega naught t? Find x of j omega. Excellent, Daniel. What is x of j omega? So this is 2 pi delta omega minus omega naught. Right? And so what do I get here, right? So therefore this is 2 pi delta omega minus omega naught times h of j omega. What is this equal to?
E raised to y of j omega, right?
Right, but this is equal to y of omega, but I'm multiplying a delta function. You have to, so I know, okay, this is equal to y of j omega, but I want to simplify the right hand side. Can I simplify the right?
2 pi h of j omega naught.
2 pi, but there's a
H
delta
of-
there as well, right? I use a sampling property, so that delta is going to stay there,
Yes, or yeah, j omega naught.
right? So this is from module 1, right? It's as we're not in the time domain anymore, but we're in the frequency domain, right? So this is a sampling property of the unit impulse, right? And but then clearly, if I take the inverse Fourier transform for this, I know from the convolution property that the Fourier transform is just simply going to be equal to right? So ये क्या है? ये constant है. It's not a function of omega anymore, but it's only a function of omega naught, and omega naught is a constant, right? So it's just a constant there, right? So it's a constant being multiplied by 2 pi omega minus omega naught, right? So this 2 pi omega minus omega naught is the Fourier transform for what? As we've just seen, this is the Fourier transform. This is the Fourier transform of e raised to power j omega naught t times the constant, and linearity kicks in, and therefore y of t must be equal to e raised to power j omega naught t times h of j omega naught. Right, so everything clicks together, right? So that's why the product or the convolution property is much, much more general. You can derive everything from here. Is this clear? How I got to how I got from here to here?
Yes, sir.
Right. If anyone's confused about that, you can ask me now. Right. So once again, the principle is h of j omega naught is a constant, and linearity kicks in. If I take the inverse Fourier transform of that, inverse Fourier transform is just going to be h of j omega naught times the inverse Fourier transform for this, which is e raised by j omega naught t. Right. So that's your proof there. All right. Now I was talking about, so let's do another example, right? Or rather application in frequency selective filtering. And I can set this up with many related yet different applications. All right, so here's one of those. Let's say I give you an audio signal, right? And I know that the desired audio signal, for example, that could be my speech, is between, let's say, 8 kiloradians per second and minus 8 kiloradians per second, the Fourier transform for that, right? But I know that there's this extra bit of noise or interference which resides at high frequencies, right? So if I try to visualize this, so let's say there's some x of j omega. So this is x of j omega, right? And the Fourier transform for this x of j omega looks something like this. Something like this, right? An arbitrary shape, right? Which is in between minus omega c, which resides between minus omega c to plus omega c radians per second, right? So this is the desired or the signal of interest. For example, this could be vocals, right? But then there is an extra bit of interference that is high frequency here, right? This could be, and I'm going to put up a demo on LMS as well. This could be, for example, high frequency noise, for example, dog whinings, right? Which reside at a frequency which is greater than omega c, right? Now, if I would just look at this signal in the time domain, there is going to be no visible difference or distinction between what my speech looks like and what this unwanted interference looks like. Right, so this is this, and this is the same interference, right? So in time domain, I would have found it very, very difficult to be able to find a distinction or to be able to find a distinguishing feature between these two types of signals, right? My job is to do what? My job is to design a system, an LTI system, which can extract for me the signal of interest and block all the unwanted interference in the high frequency domain. The convolution property, because I'm now familiar with the convolution property, that enables for me a very, very intelligent sort of a design. It's a very design. I can come up with an LTI system very, very easily, which would let me do that, right? Can anybody take a guess on what kind of an LTI system would that look like? So the question is the following, right? So the question is, can one design an LTI system that can extract the signal of interest while blocking the unwanted interference? What do you think? Who can come? Low pass RC, right? So I'm given complete flexibility here, right? So Umar, you say low pass RC, yes, that's a system, but it would not be able to completely cancel the unwanted interference, right? I want something which would be able to completely cancel the signal of interest. And Daniel says a band pass. What do you mean by a band pass, Daniel?
Sir, वो lower और higher frequencies दोनों को करेगा ना filter out.
Right. So
दोनों sides पे noise है.
दोनों side पे noise है. Okay, but remember, this one of the axes is the positive axis and the other one is the negative axis, right? Why do I have a symmetry around here, by the way?
So sir, वो फिर add up होके उसका exponential part cancel हो जाता है.
Yes, so let me assume that x of j omega. I'm assuming that the signals are real. Excellent, Umar.
Okay.
Right? I'm assuming the signals are real, and because of that, there is a symmetry in the positive and the negative axis, right? So the positive frequencies and the negative frequencies, the absolute for that are identical, right? So I want to extract the low frequencies and block out the high frequencies. And when I say high frequencies, so minus, for example, this could be, let's see here. This frequency here is, let's say, omega high, and this is minus omega high. So minus omega high, I would treat that as a high frequency as well, because the oscillation rate is the absolute value for that. Okay? So I want to extract the signal from minus omega c to plus omega c, right? Usko kisna extract kar sakta hu main? What kind of an h of j omega should I be looking for? Right? Excellent. Right? So Umar says a square pulse. Umar, square pulse जो है in the time domain or the frequency domain?
Frequency में.
Frequency में. उस square pulse का magnitude कितना होना चाहिए?
X of j omega naught का जो absolute is magnitude of non-constant. नहीं बल्कि 1 होना चाहिए.
Sorry, उसका height क्या होनी चाहिए? h of j omega.
उसका height 1 होनी चाहिए ताकि वो x of j omega को vary ना करे.
Excellent. और उसकी कट ऑफ कहाँ पे होनी चाहिए? इसका मतलब कि पल्स जो है कहाँ पे खत्म होनी चाहिए?
वो माइनस ओमेगा सी से पीछे होनी चाहिए और ओमेगा सी से आगे होनी चाहिए.
Excellent.
और ओमेगा जहाँ पे स्टार्ट हो रहा है उससे पहले होनी चाहिए.
Right. So I can do this with right? So let me try a feature here. So I can do this with this kind of h of j omega. If I choose the LTI system with the frequency response that looks like this, right? So this is plus omega c and this is minus omega c and the height is 1, right? And this is called an ideal low pass filter. Now, I think, Daniel, you said something about a band pass, right? So I just want to make things clear here. This filter that you see on your screen, even though it may look like a band pass, क्योंकि यार वो minus omega c or plus omega c का band pass, this is not a band pass. This is a low pass filter. Because why is it called low pass filter? Daniel, you want to venture a guess? I would say that this is still a low pass filter. Why is that?
Yes, sir. वो सिर्फ हम लोग पॉजिटिव साइड पे अगर देखें तो फिर
Yes,
low.
exactly. So for me, as far as all the frequencies around 0, whether they be positive or negative, I would categorize them as low frequencies, right? And the high frequencies are the omega h or the minus omega hv. So there's symmetry around the origin, okay, as far as low and high frequencies are concerned, right? So this is an ideal low pass filter. And if I design my LTI system to have a frequency response given by this square pulse, this would be able to completely cancel out the unwanted interference and extract my signal of interest, as Umar, I think, suggested, unharmed, unchanged, because the magnitude is 1 or the height is 1, right? So what would be the this is the frequency domain, right? So now you're designing everything in the frequency domain. So the frequency domain now allows us a tool which, or is a design criteria, if you will, or tool for design, right? Even though things are always going on in the time domain, right? Convolution हो रही है, system है, कोई RC circuit है. I mean, signals are coming in the time domain. The filters or the LTI system also work in the time domain. Yet the design takes place in the frequency domain, right? We want the time domain LTI system, the impulse response, to be such which ensures that this frequency response looks something like this ideal low pass filter. The question is, what is the impulse response of such a filter, right? And in order to determine the impulse response of this such ideal low pass filter, all I'm going to do is just compute the inverse Fourier transform for this, right? Which is minus infinity to plus infinity, h of j omega e raised by j omega t times dt. And we've done this already, by the way, okay? Which is a sinc function, yes, you correctly point out. And just let me write down the result directly. This is sine omega ct divided by pi t, right? And in the time domain, this looks like a sinc, right? Something like this. A decaying sine, if you will, linearly decaying sine. And the first cutoff is going to be at pi by omega c and 2 pi by omega c and so on and so forth. Okay? Now, there are practical problems with this, by the way. Can you point out some practical problems for this? So this is, I mean, all of the things that we said, Kiji. This is the ideal low pass filter. What kind of a practical problem do you see in this filter?
सर कि बहुत मतलब sharp है और अचानक से एक बहुत बड़ा impulse सा आता है.
Okay, exactly. So the frequency domain is very, very sharp. And it turns out it's because of that sharpness, the time domain complexity, if you were building this with a circuit, the time domain complexity that you require is going to be astronomically large, right? So practically speaking, we can never achieve this frequency response, right? And other practical problems, one of the other practical problem could be, okay, this filter is actually not a causal, or this LTI system is not a causal system. That's clearly visible, right? It's not a causal system. And the reason why it's not a causal system is because the impulse response is not equal to 0 for t is less than 0, right? And practical systems can never be non-causal, right? So that's one of the other problems, right? So the filter design is a whole new dimension, or is a whole different dimension, something we don't have the time to dig into. But this, I just want to touch some things over here. Practically फिर RC आप use करते हैं और RLC use करते हैं, and then multiple stages and so on and so forth, right? First order, second order, third order, and higher order, right? So it is because of that convolution property that that allows us to design these frequency selective filtering, right? To cancel things out, to extract things out, and do a lot of other things. I mean, I recall something about saying something about equalization a while ago. ठीक है? Equalization क्या होती है? कि there's some frequency components in your audio speech that you want to amplify more than the others, right? And since, I mean, all of that thinking process is going on in the frequencies, कि ये vocals low frequency पे हैं, bass जो है उसे और भी low frequency पे है, तो you want to amplify the bass, so it's a high frequency, low frequency पे gain ज़्यादा कर दें, और vocals वाले पे बहुत ज़्यादा ना करें लेकिन कम कर दें, उसे high frequency और भी कम कर दें. So you could imagine a system which is not just this flat thing, but in different regimes it has different gains, and that's called equalization, right? So frequency domain analysis and this convolution property, it is because of that you come up with those designs. Okay. All right, and we've done a lot of interesting exercises, by the way, in EE100 for freshman courses. What the kind of things that you could do in the frequency domain. Right. One simple example I can give you, not for E100, I say, okay. So medical instrumentation, for example, if you're measuring your EEG, which are your brain waves, right? The voltage that's coming in from those EEG signals are extremely small, right? In the order of microvolts, right? And then you want to amplify them, और फिर amplifiers लगते हैं, उसको बड़ा किया जाता है. लेकिन बड़ा करते करते what happens is you always get a 50 hertz noise there, right? 50 hertz interference. Any ideas where that 50 hertz interference comes from? क्या ख्याल है 50 hertz interference कहाँ से आ सकती है? CEP से कुछ ताल्लुक है उसका? Yes, your main line or your AC voltage, right? The AC voltage, which is coming out from the main line, causes electromagnetic interference, and that is picked up by that amplification, and you need to cancel it out, right? So मेरी आवाज आ रही है सबको? I think my video is frozen.
आवाज आ रही है, वीडियो फ्रोजन नहीं है.
वीडियो फ्रोजन है या चल रही है?
फ्रोजन है अभी.
फ्रोजन है.
वीडियो फ्रोजन है सर. आवाज ठीक है.
Okay. Any questions about this before I talk about the next example, which is once again going to be an application which is not frequency selective filtering anymore, but another way to compute convolution, if you will, right? So this is another example. And so you could use a convolution property to compute convolution as well, right? So here's how. Let's say I give you x of t, which is e raised to power minus bt u of t. And I give you h of t, which is e raised to power minus at u of t. And I ask you to compute, so where this, what's going really on is x of t is an input to an LTI system, which has an impulse response h of t, and the output is y of t, right? and you need to determine what y of t is. So essentially you need to compute this convolution, right? Now, one of the ways to do this is to go into the Fourier domain first, right? Do that multiplication and then compute the inverse Fourier transform to get what the convolution would have been, right? It's just like that example that I gave you earlier, right? In order to find solutions in country A, you often have to go into country B, which provides you with a shortcut. And this frequency selective filtering, the idea that I just mentioned up above, is exactly that, right? So every operation is actually going on in the time domain, which was country A. But in order to get more insights, to get a shortcut, if you will, right? You take that short path through the Fourier domain, which is country B. Design everything in country B, and once you have the design, then you go back in country A, and the solution once again exists in country A. This is exactly what we're going to do in this example as well, right? So what we will do is we will compute the Fourier transform of x of x and h, and this it turns out to be equal to, I'm not going to compute this here, this is 1 upon b plus j omega, right? This is the very first example that we did, I think, when we computed the Fourier transform, right? This is the Fourier transform of a real exponential. And of course, what's given is kg a is greater than 0 and b is greater than 0, right? And h of j omega is 1 upon a plus j omega, right? And therefore, y of j omega is going to be equal to x of j omega times h of j omega, right? And therefore, this is equal to 1 upon a plus j omega times b plus j omega, right? I need to compute y of t. What do? I compute the inverse Fourier transform of this y of j omega, right? How do I do that? How do I compute the inverse Fourier transform of y of j omega? क्यों तला? क्या ख्याल है?
So y of j omega निकाल.
Yes. You'd have done this a whole lot.
अच्छा नहीं, actually I wasn't pre-guessing और मुझे कोई आ गया था.
Okay. Anybody else? Circuits 2 में सब कुछ यही करते रहे आप लोग. I need to compute the inverse Fourier transform of y of j omega.
So partial fraction करेंगे पहले.
Yeah, partial fraction expansion करेंगे, right? So this is exactly what you did. Circuits with Laplace transform, right? So this is, I do a partial fraction expansion. This is capital A upon a plus j omega plus capital B upon b plus j omega. And if you are not comfortable with partial fraction expansion, right? So, but Hassan, I'm sure you're very comfortable with partial fraction expansion, right? So if you're not, anyone is not comfortable with partial fraction expansion, I've shared the background material needed at the very, very beginning of the first class. That's up there on LMS. You can take a look. I mean, it has a separate section on partial fraction expansion, right? So all I need to do now is to find capital A and capital B. Tareem, what do you mean by that? Can we simply inverse x of j omega to find y of j omega?
सर जिस तरह से जो भी हमारे पास x of j omega आ रहा हो, जब हमने y of j omega फाइंड करना तो हम 1 over x of j omega करते हैं सिंपली, तो फिर हमें इतनी लंबी कैलकुलेशन नहीं करनी पड़ेगी.
नहीं, at 1 upon x of j omega से क्यों हो जाएगा? So we need to find the inverse Fourier transform, right? So I need to find the inverse Fourier transform for this, whatever this function of omega is. Right, so 1 upon x of j omega, I'm not exactly sure what you mean by that. Achha, chale. So how do I determine A? So A is just equal to y of j omega times A plus j omega with j omega evaluated at minus a, right? That would ensure that the b cancels out and you're going to be left with a. And therefore, this turns out to be equal to 1 upon, so I'm skipping steps here. This is 1 upon b plus a, b minus a, sorry. Okay, so I'm just plugging this in here in equation number 1. Right. So what about b here? Capital B is just simply going to be equal to y of j omega times b plus j omega. With j omega, you just plug in that equal to minus b, and this turns out to be equal to 1 upon a minus b. Okay, so this is what a and b is. And by the way, this holds true only when b is not equal to a. Otherwise, you're going to run into trouble. When a is not equal to b, you have a 1 upon a plus j omega whole squared, and that's you can't do a partial fraction expansion on that. You do something else. All right. So then y of j omega therefore is equal to 1 upon b minus a. This is 1 upon a plus j omega minus 1 upon b plus j omega. So what's the inverse Fourier transform for this? What is y of t? What do you think y of t is?
A sinusoid.
Sinusoid, why a sinusoid?
सर CEP में भी ऐसा ही एक्सप्रेशन था, तो उससे हमें साइनोसाइड मिला था, तो गेसिंग
CEP में इस तरह का एक्सप्रेशन शायद नहीं होगा, उसमें यहाँ पे एक्सपोनेंशियल्स आ रहे होंगे कोई ना कोई.
Okay.
Right, so I need to compute the inverse Fourier transform, right? So inverse Fourier transform, Fourier transform is linear, and I know for a fact that 1 upon a plus, chale, e raised to power minus at u of t ka Fourier transform is 1 upon a plus j omega, and I have some answers in the chat box. Excellent, right? So there's a Umar, you're missing a you're missing a u of t there. Right, so Hassan, this is not exponential, complex exponential. There's a u of t there as well. So वरना जो complex exponential का Fourier transform delta होता है, right? It's not absolutely integrable, right? So this is 1 upon b minus a, and as Omar rightly pointed out, this is e raised to the minus a t u of t minus e raised to the minus b of pt u of t, right? And you can go ahead and compute that convolution, and you will find that the y of t from that convolution would yield the same result, right? But this is the case only when b is not equal to a, right? So we would have to deal with the case for b equals a separately. So when b equals a, y of j omega is actually equal to 1 upon a plus j omega whole squared. I need to find the inverse Fourier transform for this, right? How do I find the inverse Fourier transform of this? I'm going to use some properties here. The differentiation property in particular, which is I know for a fact that e raised to a minus at u of t yields Fourier transform which is equal to 1 upon a plus j omega, right? ये 1 upon a plus j omega को अगर मैंने स्क्वायर करना है नीचे, right? तो what do I do?
Multiply with t on the left hand side.
Excellent, right? So this is one of the properties that we did in the last class, which was, recall, which was a property, that t times x of t has a Fourier transform which is equal to j times d of d omega x of j omega. Right, so this is a property that we did last time, right? Which is a differentiation of the frequency property. And I can therefore say that the Fourier transform of t times e raised to the minus at u of t is going to be equal to j times d by d omega 1 upon a plus j omega. So what's the Fourier transform? What's the derivative here? So derivative of 1 upon a plus j omega is a plus j omega whole squared. There's a -1 because of the power, and then there's a j because वो j के साथ multiply हो रहा है, right? And j squared is -1. -1 is going to cancel with -1, and therefore this is equal to 1 upon a plus j omega whole squared, right? So in this case, so this implies that when b equals a, y of t is going to be equal to t times e raised to the power minus at u of t. All right. Any questions here? Now, I can give you another example because, I mean, for the example that I just did, you could say, yeah, I perhaps find convolution a lot easier than computing this Fourier transform. Why don't I just work with convolution? Convolution karta hu, right? I mean, why do I need to go into country B? I mean, this country B seems a longer path, right? The following example is going to provide you with a reason country B, or which is a Fourier, is indeed a shorter route. And here's why. So let's say there's x of t, which is equal to sine omega 1t divided by pi t. And there's h of t, which is the impulse response of the system, which is sine omega 2t divided by pi t, right? And I ask you to compute, this is the exercise, compute y of t equals x of t convolved with h of t, right? Convolution करके दिखाएंगे इधर, right? And when you start doing this convolution, just applying the convolution definition, and things are going to get tough. I mean, I'm not saying it's not going to be doable. It will be doable, but things are going to get tough, right? However, it's a lot easier to, very, very easy to do in the Fourier domain, right? So through the country B, and that's going to provide you with a very, very, is a shortcut, right? So x of j omega, I know from the analysis that I just did for the low pass filter, is x of j omega is actually a rectangular pulse, which resides between plus omega 1 and minus omega 1. Right? If this is omega, and h of j omega is exactly that. It's the same rectangular pulse, except that this is from minus omega 2, the cutoff is omega 2 radians per second, right? So y of j omega is what? Y of j omega is just simply equal to the product of x and y, h, right? So what would this product be? I mean, when I multiply these two square pulses together in the frequency domain, what would you get?
x of j omega ही आ जाएगा, लेकिन उसका magnitude जो है वो scale हो जाएगा.
Right. So okay. So the magnitude is 1 here, and the magnitude here is 1. And the height is 1 for both pulses. Right.
x of j omega ही आ जाएगा.
Right. Umar says के अब क्या कहेंगे?
x of j omega ही आ जाएगा दोबारा.
X of j omega. Why do you think x of j omega आ जाएगा?
वो मल्टीप्लाई होंगे, ओमेगा 2 अगर बड़ा है ओमेगा 1 से,
हाँ,
तो वो 0 होगा उन पॉइंट्स पे, एक्स्ट्रा पॉइंट्स पे, तो वो मल्टीप्लाई होकर 0 हो जाएगा.
Yeah.
और जिन पे वो ओवरलैप करेंगे तो वो बेसिकली क्योंकि 1 ही है वैल्यू तो 1 ही रहेगी.
Right, excellent. Right, so there's a whole lot of responses in the chat window as well, and which are correct. I mean, for example, the Anyal says it depends on omega 1 and omega 2. Yes, it depends, right? And it depends on which one is bigger and which one is smaller, right? So this y of j omega, when I do that multiplication, is going to be equal to a square pulse again. But the limits are going to be, this limit is here going to be the minimum value between omega 1 and omega 2. Right? Because depending on which one is smaller, I mean, that's going to cancel out or block out the other one. Okay? Or similarly here, this is going to be minus the minimum of omega 1 and omega 2. And consequently, what is y of t here? So I did not have to do any convolution. I can just quickly write down what y of t is. Y of t is sine minimum omega 1, omega 2 times t divided by pi t. Right? So where this is inside the sine. This is inside the sine. Right? So I mean, this should drive home the point K at many problems. Going through this route of computing the Fourier transform and then the inverse Fourier transform is often a lot easier than computing the convolution, right? Not always, but many times. All right.
मैं पता कैसे चलेगा what's better route?
So I mean, if you come across the only way you will find this is when you do the problems. I mean, बगैर किए कुछ नहीं पता चलता.
So just practice and
That's practice,
then you
right?
establish an instinct for it.
Right. So Tala, अगर ये देखें, there's a sine omega t in the numerator and then there's a pi t in the denominator, and you clearly see कि इसके साथ integration में you're gonna have face problems because there's a denominator में t है, ऊपर sine है, right? And immediately, I mean, things are gonna get hard. So why don't you try in the frequency domain? Frequency domain, I know it's a low pass filter, and that makes things easier. Okay.
Okay, thank you.
All right. So any questions about this? All right. So what I want to do next, rather quickly, is the multiplication property, which is also important. And I am not going to do a proof for this, right? So the property is the following, right? So if there's a signal S, if I say कि R of t is S of t times P of t. So now instead of doing convolution in the time domain now, I'm doing multiplication in the time domain, right? So the question is कि the relationship between R of j omega, S of j omega, and P of j omega. What is that? Right? So I'm not going to do a proof for this, but I can point you to an answer, and perhaps we found KG. Yes, so the people are already pointed towards that, right? So we found K convolution in the time domain is equivalent to multiplication in the frequency domain, right? And we've also seen very from a broader perspective, not a lot of detail, that there exists some duality between the time domain and the frequency domain. So if the convolution in the time domain is equal to multiplication in the frequency domain, multiplication in the time domain must be equivalent to what? Convolution in the frequency domain, right? And that's intuition based on duality, but you can derive the result as well based on the same principles that I used for deriving the convolution property. And I'm just going to give out the result here, which is K. If I have a signal R of t, which is equal to S of t times P of t, the Fourier transform for R, which is R of j omega, is actually equal to 1 upon 2 pi S of j omega convolution with P of j omega. Right, so there is a 1 upon 2 pi here. So the duality, remember, because the Fourier, forward Fourier and inverse Fourier transform, there's a difference. Slightly, there's a 1 upon 2 pi there. Okay, so this is a result that we're going to use directly, and perhaps I'm going to leave the derivation as an exercise. I am going to do some examples, whatever I can do now. Which is that x of t, if I give you x of t, which is equal to, y of t equals x of t e raised to power j omega naught t, where omega naught is a constant, right? We've done frequency shifting property, right? So which is from frequency shifting property, we know that y of j omega is actually equal to x of j omega minus omega naught, right? And which is extremely interesting, which is in sense, Katie, if you want to shift your signal in the frequency domain to the right by omega naught radians per second, all you do is you just multiply with a complex exponential and it will be shifted. Okay, all of it to the right? And which is basically you can use it to somehow increase the pitch of your voice, if you will, right? Or increase the frequency of your signal, right? Just a simple translation in the frequency domain. Now, this is something we know from, and we did in the last class, right? The question is derive the property using the multiplication property. So how do you do that? So derive this result. Right, so that's pretty straightforward. I know that there's x of t times e raised to power j omega naught t. If I compute the Fourier transform for that, I know from the multiplication property, this is going to be equal to 1 upon 2 pi x of j omega convolution with the Fourier transform of e raised to power j omega naught t. Right, so this is something I know. Right, and फिर ये क्या बनता है? This is 1 upon 2 pi x of j omega convolution with the Fourier transform of e raised to power j omega naught t is equal to what? So I realize there's quite a bit of lag. Okay, is equal to 1 upon 2 pi delta omega minus omega naught. Right, so what is this equal to? This 2 pi, sorry, there's a 2 pi here. So this 2 pi cancels with this 2 pi because of linearity of the convolution operation, and x of j convolved with delta omega minus omega naught is just equal to x of j omega minus omega naught. Right? Pretty straightforward. Let me do another example. And which is y of t equals x of t times cosine omega naught t. Right? Have you come across something like this ever? Okay, when you take up a signal x of t and then you multiply with the cosine, what does this do? I mean, what does this do? कभी देखा है? So this is called amplitude modulation. Or the short form for this is AM, right? Yes, Salah, आपने कहाँ पे देखा है?
सर इसमें अगर हम वो कर रहे हो यानी e raised to power t से मल्टीप्लाई over x of t is e raised to power t, so we have the dampening या फिर expansion. So what I was saying was कि ये जो हसन ने बात की है कि x of t is forms an inner wave outside of cosine of t.
Yeah.
So basically ये cosine ही चल रहा होता है, but it is उसकी shape x of t की तरह हो जाती है. So yeah, that's what you said. Amplitude उसका x of t का होगा, लेकिन shape cos वही होगी.
Right. So you may have heard of AM radios, right? पुराने ज़माने में थे, अभी भी होते हैं. Right. So Radio Pakistan, I think, still broadcasts in the AM band. तो
मेरे पास पड़ा हुआ है एक मैंने यूज नहीं किया, मुझे अभी मिल गया था कुछ ये दोनों.
Yeah. So I mean, the technology that they use is exactly similar. What they do is whatever the sound wave is, sound signal is, roughly speaking. I mean, there's some other things going on as well. There's a sound signal have x of t है, and they just multiply that with a cosine, right? And what that cosine does is, if for example this is x of t, and the cosine omega naught t is typically of a much higher frequency than the rate at which the signal varies, and therefore as you suggested कि यार वो envelope बन जाता है, right? And so this is what the y of t looks like, and y of t का जो envelope है वो x of t बनता है. Right, so this blue thing is x of t, and this is y of t, right? And this blue thing here is at the bottom is not necessarily x of t, उसका सिर्फ envelope दिखाने के लिए किया हुआ है. Right, so this is how you do amplitude modulation. But what's important, what's interesting is what happens in the frequency domain, right? What happens in the frequency domain? What happens in the frequency domain is if I just apply the Euler's identity, so y of t is half x of t e raised to power j omega naught t plus half x of t e raised to power minus j omega naught t. And now you can use either the convolution property or the frequency shifting property to conclude that y of j omega is going to be equal to half x of j omega minus omega naught and plus half x of j omega plus omega naught. Right? So essentially what you've done is that if this was x of j omega, and for example your audio speech or audio signals are baseband signal in the sense that they reside at lower frequencies, right? Around the baseband, right? So this is called baseband. What would y of j omega look like? क्या ख्याल है? What would y of j omega be?
सर इस तरह के तीन होंगे, दो होंगे.
दो होंगे exactly. किधर होंगे?
सर एक जो होगा राइट साइड पे होगा उसमें माइनस ओमेगा नॉट वाले.
Right. Excellent. Right. So एक होगा लेकिन उसका amplitude half होगा उससे.
Half हो जाएगा.
Right. So let me draw a smaller one here. Weight तो उसकी exactly उतनी है, but the height is smaller. Right. So this is omega naught and this is minus omega naught. Right. So what you have done is you have increased the frequency of your signal, right? And this is y of j omega. And what you transmit over the air is actually y of t and not x of t, right? And there's a particular reason why you do that. Any ideas why? It's called amplitude modulation. Why do you need to amplitude modulate? I mean, उसी को audio signal को ही antenna के ऊपर क्यों नहीं डाल देते?
वो loss minimize कर देता है किसी.
Loss minimize कर देता है? What do you mean by that?
Over long distances जो होता है, जो कम frequency होती है वो over long distances नहीं travel कर सकती.
Actually, it's the other way around. जो high frequencies होती हैं वो ज़्यादा attenuate होती हैं over long distances. This has to do with electromagnetics, right? So it turns out that you may or may not have come across this, the antenna size that you need to transmit a radio signal, that is dependent on your wavelength or dependent on the frequency. The larger the frequency, the smaller the antenna size required, and vice versa, right? इसलिए baseband को transmit करने के लिए you need a very, very large antenna. High frequencies को transmit करने के लिए you need a smaller antenna, right? And that's why your the Wi-Fi 2.4 gigahertz के ऊपर जो हमारे antennas phone के अंदर है, they're not visible even, right? When otherwise पुराने handsets में remember वो या radios के ऊपर AM radios शायद आपको याद हो, अभी जो तलहा कह रहा है उसके ऊपर से एक antenna निकलता होगा लंबा सारा, right? That has to be big in order to get a good reception.
Sir, actually, what I was thinking, मैं पूछना था आपसे कि actually जो the one I have, it has a rectangular antenna instead of a normal straight antenna.
Okay, so there are different types of antennas, and we don't want to go into a lot of detail there. In general, for transmitting low frequencies, you need larger antennas. For transmitting high frequency, you need smaller antennas. And that's why this comes in handy, this process of amplitude modulation, which just basically translates your signal in the frequency domain. Okay. And this is also important from another perspective, which is कि आपके स्पेक्ट्रम जो है जो अवेलेबल है इन पाकिस्तान टेलीकम्युनिकेशन अथॉरिटी लाइसेंस करती है, राइट? सो यू नीड यू पे अ लॉट ऑफ मनी. सो फॉर एग्जांपल 4G स्पेक्ट्रम और mobile operators, they pay a lot of money to get license to that spectrum, and only they are allowed to use it, right? So you have different frequency bands in which certain operators can transmit and no other can do that, right? So इसका मतलब आपको frequency domain में आगे पीछे चीजें करने की जरूरत पड़ेगी, right? So if, for example, this could be Warid here, and this could be Telenor here, right? And they don't overlap in the frequency domain. That means कि उनको आसानी से अलग किया जा सकता है, and the separation is maintained in the frequency domain. So once again, the Fourier transform, the ideas of Fourier transform become very, very handy to be able to separate them out. Okay? So that's why these ideas are so powerful, right? So I'm going to stop here and take questions if you have any. Yeah, any questions?